Once again, we're going to come back to a graphical representation here that's useful, and in this case it's a force time graph, and hopefully you're becoming aware already of the fact that graphs can show us different things depending on either the gradient or the area under the curve. In this case we're going to consider the equation that we saw in the previous video, that force is equal to delta P on delta T. So just to link into that idea. So that means if we have a force time graph where force is on the vertical axis and time is on the horizontal, if we look at a very simple situation of a constant force being applied for a given period of time, we can see, based on this equation and based on the impulse that we saw last video, force times change in time gives us that impulse delta P. So in this case, for a graphical representation, the area under a force time graph gives the impulse. And again, rearranging that equation, can see that F delta T is going to give us that value of delta P. So on this graph on the left here, let's say we were looking at the time that from this point to this point. So we'd be interested in going from, say, time T1 to time T2. That area that we would calculate under there would give us the change in momentum delta P for that change in time. So you can consider that the time that we would have in this direction here would be the value delta T. So fairly useful one there, that as the force varies, or as the force is measured over time, the area under that graph gives us the impulse, which in other words is the change in momentum of whatever the force is being applied to. That's a very straightforward situation, but in reality forces are very rarely applied at a constant rate. So many situations involve varying forces. And just to think of one that it's fairly easy to relate to, think about say jumping, the force that you apply to the ground. As you sort of compress your legs, you start pushing on the ground. You'd be pushing, that force would change over time, would increase and then decrease again as your feet start to lift off the ground. So in that sort of scenario, the graph for force versus time will look a little bit different. Won't be a constant force that's being applied now. The force will vary, and so what we would expect to see is something like the force would increase to a maximum and then decrease back down again. Again though, we could calculate the area under that graph to figure out the change in momentum that would occur as you would be sort of pushing off the ground to jump up into the air. Now in this case, because that area is now a triangle, let's say that this force up the top here will give that denote that as F max. The change in time is still going to be this change in time that we're dealing with here, so that would be delta T. In this situation, it's not just a case of multiplying the two quantities, F max times delta T. We'd need to calculate the area under the curve. So that would be half, so area of a triangle basically, so half F max multiplied by delta T. You could sort of think of that as being a situation where half of F max is kind of the average force. So basically what we're doing is converting that into a rectangle, where we've sort of chopped these triangles and we've sort of swung half of it that way and swung half of it that way, and that value there would then be F max on 2. So just a way to sort of make sense of what that calculation is actually doing. It's sort of leveling it off to a constant force. That still is somewhat a simplified scenario, and just briefly take this one step further. if we had a situation where the force varied in somewhat unpredictable ways, so these sorts of situations, I don't know, you could think of any number of random scenarios where force is being applied that's not particularly constant, and it might sort of vary depending on what's happening in the way that the force is being applied. In this case, there's no mathematical relationship that we can refer to easily. So there's no mathematical relationship between F and T. So what we can do in that situation is literally just sort of approximate the area. So the area can be approximated, and that can just be, imagine that was graphed on a piece of graph paper, so we can approximate it by what sort of that process of just counting the squares. So counting up how many squares are under that curve, or we could approximate some shapes. So approximate geometric shapes. And what I mean by that is, for this scenario, we could sort of approximate that there's a triangle here, roughly speaking. Could then consider the next bit to be a trapezoid, and then almost rectangular up to that point, and then maybe another triangle through here. So just by making rough estimations of the shapes that are involved, you can then figure out fairly reasonably what the area under the curve would be there, and then the total of that would be the change momentum delta P.